Good evening. How's the volume? Everybody good? Okay. I'm Angela Mettler. I'm an administrative assistant in the president's office at the South Dakota School of Mines. And welcome. Thank you for coming, especially for braving the extremely cold weather that's just going to get worse. So I'm kind of glad this is happening tonight. Steam Cafe is a partnership with South Dakota Mines, South Dakota Public Broadcasting, and Hay Camp Brewing. We could not do it without them, and we can't do it without you. So we're very glad you're here. Thanks also to those of you who are attending online. If you have any questions, there will be a question and answer session at the end. Those of you who are attending online can either type your question in the chat or ask it at the Q&A, and I will ask it live and it will be answered live. Yeah, I think that's pretty much it. So tonight's presentation is going to be done by two presenters, one of whom is attending virtually. So the virtual presenter, her name is Dr. Rachel Benton. She will be starting the presentation. You should be able to hear her through the speakers. You're probably not going to be able to see her super well. She is up in the upper right-hand corner of the presentation waving. I don't know if you can tell. Yes, but she will start, and then Nate will take over at some point. So just so you're not wondering who's talking when Dr. Benton is on. She's attending virtually. So I will turn it over to you, Dr. Benton.
All right, thank you, Angela. The title of our talk tonight is the National Park Service Paleontological Collections Fund, Conservation and Preservation of NPS Fossils housed at the Paleontological Research Laboratory. And I am recently retired. I worked at Badlands National Park for 24 years. And one of our biggest challenges was to find funding to curate, prepare, and store fossils. The National Park Service houses thousands of fossils at the different NPS units. And this is a major obligation of the Park Service that we take very seriously. Next slide, please. Okay, and just a general outline of our talk tonight. We'll introduce our topics here, and then we'll talk about different conservation methods used with fossils, NPS fossils housed at the PRL. We'll talk about microfossil processing, collection matrix and digitization, trying to get all fossils and all their associated paperwork digitized and into Specify. We'll talk about that a little bit later. And then also collections research going on at the School of Mines and the PRL. Next slide. I set up this fund in honor of my parents, Norma and Dwayne Benton, to continue their spirit of philanthropy. And I have donated a portion of their estate to support the National Park Service Paleo Collections Fund at the School of Mines. My parents were always very supportive of my work at the School of Mines. I am an alum. I graduated in 1991 with a master's in vertebrate paleontology and went right into the Park Service as a park paleontologist. Next slide, please. So we set up the fund with the School of Mines Foundation, and the purpose of the fund was to curate, conserve, prepare, also support field excavation and research of National Park Service paleontological collections at the PRL. And most of the fossils that are housed at the PRL with the National Park Service are from Wind Cave National Park and also Badlands National Park. The fund also supports the salaries of students and staff working on the various NPS fossils supported by this fund. The fund also goes towards equipment and supplies for National Park Service collections. It's also a tuition remission for graduate research assistants on projects that they work on supported by the fund. And we started in May of 2019, and this will continue through 2022 and hopefully beyond that as well. So, and that's my portion of the talk. I'll pass it over to Nate.
Thank you, Rachel. Okay, so I'm going to jump into some of the current projects that we've been working on through the NPS Fund. Those are going to mostly focus on Badlands National Park and Wind Cave National Park, as Rachel mentioned. Within Badlands National Park, the locality that we've been focusing on for the last 3 years, it's been the Big Pig Dig. Never say that. At Wind Cave, we have the Beaver Creek Rock Shelter and then Salamander Cave. So those are the 3 projects that we've been focusing on mostly. And over here, you can see this funky looking critter. It is what's called Archaeotherium, and the common name for it is the hell pig. It's how the Big Pig Dig gets its name. It's one of the most common animals that you find there, and it's one of the most common fossils that we end up conserving and cataloging in the PRL. So now I'm going to jump into conservation methods. We got a third presenter. She can't be here today. She had to travel for the holidays. So if you have any specific questions about conservation techniques that I can't answer, please follow up with her afterwards. But in general, conservation is actions to minimize the rate of deterioration on an object. There's 2 main types of conservation. There's preventative conservation and remedial. So preventative is basically taking initiatives to mitigate future deterioration to a fossil. Remedial is actively repairing damage that's been done. So believe it or not, most fossils don't come out of the ground pristine and beautiful like you see in the movies. They're usually pretty busted up, and a lot of them require some type of remedial conservation work. But even if that fossil isn't busted up and it's nice and everything, it's still subject to deterioration over time. So even a fossil just sitting in a drawer over time without any preventative care, it's going to start to fall apart and deteriorate, even without all the conditions of deposition and burial and all the destructive processes that can happen while fossils underground. So both of these are equally important, and we do both of these practices in the Paleontology Research Lab. Can y'all hear me back there? Can you hear me okay? Cool. All right. So first, let's jump into preventive conservation. We have a variety of methods for preventative conservation. One of them is cavity mounts. A cavity mount is basically, it's a cavity that you carve into a piece of foam. Ethafoam is the material that we use. You then coat that with Tyvek and put it in some type of an acid-free container, and that can go into a drawer with the specimen inside. We use these particular materials because they are what we call archival. That means they're not going to off-gas, they're not going to change in chemical composition, they're not going to deteriorate over time. We like that because it keeps the fossils in good condition. We're thinking not just good condition now and repairing them and making sure they're okay, today or tomorrow or next week, but 50 years from now, 100 years from now, etc. Other methods that we can use are jackets, so making custom jackets for fossils. This can be in plaster, fiberglass. It's usually some combination of those 2, and then with a coat of ethafoam to protect the fossil as sort of a barrier between the jacket itself and the specimen. And then also important is environmental controls. So you can have all the jackets you want, all the custom containers for your fossil to keep them from, experiencing the forces of gravity and falling apart. That's not going to do any good if you have a lot of environmental fluctuations in your building that they're stored in. So any major fluctuations in temperature or humidity are going to damage fossils over time. And so it's important to have a climate controlled building as well. And fortunately, we have that. The Paleontology Research Lab is climate controlled. So bonus points for us there. Okay, now let's talk a little bit about the remedial conservation. So basically, when you have a broken fossil, sticking them back together. The way we do this is with a glue called Paraloid B72. We like this glue because like the other materials I mentioned, it's archival. It is completely reversible. It's not going to change in its chemical composition. So let's say you accidentally glue a toe onto a hand, right? Student maybe that's working on prep for the first time makes a mistake, you can undo it. So that's why we use paraloid. We used other glues in the past. Those, some of them weren't reversible. Some of them would kind of change in composition. They would kind of yellow and destroy fossils over time. We don't use those anymore. Other techniques that we can use for remedial conservation is gap filling. So maybe you have a fossil that's kind of missing some pieces. It's crumbling. It's not completely broken in half, but it has enough missing segments, like in the picture here, that its stability is being affected. And so what we can do in that case is create mixtures of basically materials that you can fill in these gaps. So we can use Tangujo paper, again, paraloid B72, mix that with some cellulose powder and other ingredients and stick it onto the fossil, and it will adhere to the fossil. It will increase its structural stability, and it can be taken off again if necessary. Another good thing about this is it dries clear, so it doesn't obscure any of the morphological details of the fossils. Back in the day, people would put, they would have their own artistic license and reconstruct fossils based on the missing pieces. They would use plaster and other materials to try to kind of fill in missing pieces, even whole like bones or, parts of like a jaw or a skull, they would kind of reconstruct. And we don't do that anymore because, there's human error, that's always a possibility. And so we like to leave the fossils as natural as possible while increasing their stability as much as possible. And here's some pictures of our interns and student workers that have been supported through the NPS Fund, working on various fossil conservation methods. So here we have, it's Michael Nealand and Colette McAndrew, and they are, it looks like they're building they're starting a fiberglass jacket for a specimen there. And then over on the right, we have a bunch of interns that are gluing together pots. That seems kind of weird, right? Well, we do this because it's actually a great training exercise for fossil conservation. Before we throw a student into the lab and have them put together a deteriorating fossil, we want to make sure that they've learned the conservation techniques that are necessary to do that. And so to do this, we smash up pots. We can just go over to Lowe's or over to Menards and get a bunch of little gardening pots, smash them up, maybe take a couple pieces out if we're feeling evil, and then throw them into a bag and let those students painstakingly put them together. And the ones that have the patience to get through that task, we then move on to the next task. And eventually they can get into more complex tasks until they're working on some really complicated, busted up specimens. But you always start at basics and work your way up. And so here's some before and after pictures of what fossil conservation looks like in practice. So here is an Archaeotherium, again, that Hell-pig scapula. On the left is before it was underwent conservation in our lab. You can see it is in this kind of old, crusty, yellowy container. There's some tissue paper that's surrounding the specimen. That's common practice for getting a fossil out of the field. You want to put some kind of a barrier between the fossil itself and the plaster when you're removing it from the field. But it's not something you want to leave the specimen in forever. Tissue paper is acidic. It's going to deteriorate over time. It's going to yellow. It's going to crack. It's not going to be a good stable container for that specimen. And so what we did was we rehoused it. We put it into a custom-made cavity mount over here, again with that ethafoam and with the Tyvek sheet underneath. We put some, I'm assuming some consolidant was put on it to keep it from undergoing further deterioration. And at that point, it's stable enough where it can go into our drawers and our collections and it can stay there for different research and education projects. Here's another specimen. It's in pretty poor shape. So that is the pelvis of an Archaeotherium, not looking good. And so obviously needed a lot of work. That's what we did. So I think this was a project that our preparator Kayleigh worked on. You can see that after we have a nice custom-made fiberglass jacket for the specimen. It has been glued back together where it needs to be glued using that paraloid B72 and is now stable and again can be put in our research collections for different projects. Here's another really cool specimen. This is an articulated forelimb of an Archaeotherium. So we have over here, the upper part. This is the should be the humerus, the radius, the ulna, all the way down to the digits. So you're basically looking at this of the hell pig. Really rare thing to find. You don't often find fully articulated or even partially articulated skeletons. That's kind of like winning the lottery for fossils. More often you're going to find just an isolated element, maybe a little toe, or even just like a part of a toe or part of a tooth. So it's really special to get these kinds of things, and they need special care too. Same kind of situation. This fossil is in a jacket, a field jacket, with a lot of tissue paper that isn't archival, not good for the specimen long term. You can see it's starting to crack in areas. And so this specimen needs some both remedial and preventive conservation. And so that's what we did to it. We created this really, by we, I mean Kayleigh, created this really complex fiberglass jacket over here. We put some consolidants on the specimen to stabilize it, keep it from falling apart further. And again, now it's good for the research collections for different projects. So equally important as the conservation methods that we use is organization and collections, right? You can have all the repair on a fossil you want, but it doesn't really do any good if those specimens are just kind of dumped into a drawer and all their associated data is disorganized. It still can't be used for anything. And so that's a situation that we have here with this Badlands collection. We have a lot of fossils that are just in field bags. They're dumped into this drawer haphazardly. This isn't accessible, right? Somebody can't come in and study these bones in their current shape. So one of our interns came in and completely reorganized these drawers, did a fantastic job. Now all of these specimens, kind of hard to see in the photo, but each of them are either in an individual container or they're in a locked container with individual elements, and they are organized sequentially by specimen number with the numbers written on the outside. So it's really easy to find. If you just need one particular fossil from that cabinet, you can grab it now, where that wasn't possible before. So this is just as important. It's making the information accessible. Part of that is the physical organization of the specimens. The other part is the digital organization. So making sure that these specimens get entered into our digital database. That way the data is more easy to share with people for different projects, especially, some people can't come in person for whatever reason. Sometimes all they need is the digital information associated with the specimen, and we can share that if they're entered in our database. So those are the other projects that we work on in collections, is not just the conservation of the specimen, but also its curation, its organization, and its accessibility. Here's another example of that. So now we're moving on to Wind Cave. Everything else I showed you so far was Badlands National Park. A lot of those Badlands fossils tend to be larger and older than Wind Cave's fossils. And so that usually creates more issues that need conservation. So bigger fossils that are older tend to be in worse shape. They need a lot more conservation care, remedial and preventative. Smaller things, they're the advantage of things like rodents, salamanders, snakes, smaller, more recent fossils is that they're usually good to go. You'll have an element and you pop it into a container, and then that's about it. They don't have to go to the lab. They usually don't have to be glued together, with some exceptions. So the conservation that needs to happen with these specimens is usually minimal compared to the bigger, older fossils. But they have their own set of challenges. So microfossils, microvertebrate fossils, and invertebrates and plants, they tend to be really abundant, which is great for different projects. But it also is a huge challenge for curation and for organizing in collections. So if you have thousands and thousands of little tiny fossils, making sure that they're organized properly and stored efficiently space-wise, but also in a way that they can be used for different projects is a challenge. And so that's what we're working on here. This is one of the Wind Cave localities called the Beaver Creek Rock Shelter. And what we're doing here is just reorganizing all of the fossils, getting a catalog, getting them entered in the database, stored in these containers with information on the outside and inside, where they're individually bagged and labeled with a tag with all their associated contextual information so that they can be used for different projects. And this has been an ongoing project that we've been working on for the last year and a half. Rachel's actually been a huge help here, reorganizing and cataloging these specimens. So hopefully this collection will be very useful for projects in the near future. And so now that I kind of introduced the topic of microfossils, I'm going to be talking about it for the next section of this lecture. So I'm sure you're all aware of why fossils are cool, right? Especially big vertebrate fossils and dinosaurs and megafauna. I'm going to spend the next like 20 minutes or so trying to convince you all why microfossils are cool. So bear with me, Okay, so first, when I say microfossil, there's different definitions of them. In some cases, it means like microscopic things like diatoms that you can only see under a microscope. That's not what I'm talking about here. For this talk by microfossil, I'm using the more general term, which is like small fossils that are usually less than a couple millimeters large. So technically visible to the eye, but very hard to detect in the field. Usually they belong to things like small mammals, reptiles, invertebrates, all those kinds of critters. And yeah, they might not be as flashy as, mammoths, hell pigs, or dinosaurs, but they have their own uses. And some of these uses are for understanding past environments and environmental change through time. So when an animal is faced with a difficult situation in their environment, where their environmental conditions are no longer suitable for life, they have three options. They can either get up and move away, go to another habitat that has better conditions that they can tolerate. They can try to adapt quickly to those changes, or if they can't do any of those things, they die. With these small animals I'm mentioning here, oftentimes they don't have that first option of just getting up and moving away. So, things like small mammals have relatively small home ranges. They're not very large. They can't just get up and move, 20 miles to the next suitable habitat if they're facing, changes that aren't tolerable in their environment. That's especially true for plants and invertebrates. And so all of these smaller organisms tend to give you a lot more information about past environments because they are really constrained to just two choices, and that's to adapt or to die. And both of those are very detectable in the fossil record. So I have two examples here using some small mammals. The figure on the left here is of wood rats, or pack rats. It's an animal in the genus Neotoma. They're where you get the hoarding, analogy from. They tend to build middens, nests out of all kinds of different debris. They poop and they pee all over. It's kind of gross, but it's actually really helpful for understanding paleoecologies because you can pull little bones out of it and do all kinds of cool studies with it. That's not what I'm going into today. They're also cool because they themselves are sensitive to environmental change morphologically. So studies have shown that over the last 20,000 years, going from the end of the last ice age to the present day, these animals have fluctuated in body size in response to climatic changes. So back at the end of the last ice age, closer to 20,000 years ago, these animals were a lot larger. And then they gradually shrunk through time following the climatic warming events over the last 20,000 years. A similar study looking at these small mammals, but at a community level over the same time period, the last 20,000 years, saw another pretty prominent trend in these small mammals where at the community level, their diversity decreased with increasing temperature. So closer to 20,000 years ago, there was a lot more variety in the individual small mammal species that were present at this site. And then going towards the present day, that diversity plummeted right around the same time as the climate got a lot warmer during the glacial period about 12,000 years ago. Okay, so hopefully now I've convinced you why they're important. They can help us understand responses to past environmental changes in past animals, what environmental conditions were like in the past, and this obviously has implications for how we can understand how future animals might respond to environmental changes. But now I want to talk a little bit about the process of getting these fossils. So even though conserving them is relatively easy, pop them in a jar, they're good to go, or a vial rather. Actually identifying them, gathering these data are not that easy. So as I mentioned before, these fossils are very small. They're like 1 to a couple millimeters large. This isn't something that you're usually going to see when you're in the field. So if you're in the field looking for fossils, a dinosaur bone's probably going to jump out at you. Something that's a millimeter or smaller is probably not going to be seen in the field. And so the main way that we collect these fossils is a process similar to panning for gold. So basically you just grab a bunch of sediment in an area where you think there might be some microfossils, and then you screen wash it. So you put it in a giant screen, you run water through it, you let some of the sediment go through, and then hopefully, depending on the size of your screen, you're going to capture all of the larger elements, including bones and rocks and other good stuff. After that, the sediments get dried out. They get bagged, and then they're usually taken to the lab for additional screening. So you'll usually sort things out by different mesh sizes. That just makes it easier to pick through under a microscope. For some of the bigger mesh sizes, you might not need the microscope, but for a lot of the smaller stuff, you're going to want to do it at least under a magnifying glass, if not a microscope. So this is a pretty standard protocol for a microfossil collection. What isn't standard is the screen sizes to use. And this is important, right? Because maybe your study is trying to look at the community level changes in the different species that are present at a site, or their abundances, how many of them there are. That data is going to get skewed if you're not capturing all of your fossils. So what we really wanted to know here for this project is how many microfossils, or sorry, what mesh size do you need to capture all of the microfossils at your site? So that jumps into the objectives of our project. This is a project that we conducted over the summer as part of the summer internship that we do every year at the Museum of Geology that is supported by the NPS Fund. And our goals were to determine what the optimal mesh size is for sorting these microfossils. And so, as I mentioned, there's nothing that's really standard for this. Some studies suggest a millimeter or larger. Others suggest it to go down lower than 0.2 millimeters. So we want to know what we needed to capture all of the microfossils that we're then going to curate and use for research at our paleontology research lab. And so the objectives were to evaluate taxonomic richness and diversity. So I'll just give you a quick ecological refresher. These are kind of similar metrics, but they're not the same. So taxonomic richness is the number of individual species that you have. So like, let's say you have a site that has grasshopper, rabbits, and snails, right? So that would give you taxonomic richness of 3 if you have those 3 things. Diversity also takes into account evenness. So it's taking into account the numbers of taxa that you have, but also how evenly distributed they are. So let's say you have now 2 sites. One has, what did I say, 2, did I say grasshoppers, rabbits, and snails? Yeah. Okay, so let's say you have 2 of each of those, right? And then you have another site that has 10 grasshoppers, 1 mouse, 1 snail. The first site is going to be more diverse because it has, they have the same taxonomic richness, but it's more evenly distributed. So it's ultimately the more diverse site. This is going to be important later when I show you some figures. And so this pilot study was conducted on matrix from the Beaver Creek Rock Shelter, which we talked about earlier. As you can see with all those microfossils, it's really rich in these. There's a lot of sediments that are highly fossiliferous. And so that's why we chose this site for this study. And so for our study design, each student intern was given a gallon matrix bag. Doesn't seem like that much, but it actually takes a long time to pick through when you're under the microscope and pulling out all of these tiny itty bitty little fossils. And so they were then tasked with sorting the fossils into 4 mesh fractions that we were examining. So the largest one is going to be a pan with a mesh container that's larger than 4 millimeters, so really big stuff is going to be captured there. And then going down, we also had a 4 to 2 millimeter mesh screen, a 2 to 1 millimeter mesh screen, and the smallest one was the 1 to 0.5 millimeter mesh screen. That smallest one is really important because we want to know if we're actually even seeing any fossils that are smaller than 1 millimeter. If not, it might not be worth our time to pick through it, but maybe it is. And so that's what we're testing here, is if we have to go down to 0.5 millimeters to capture all of our small fossils at this site. So again, we're evaluating the taxonomic diversity and richness per mesh fraction per bag. And each one of these bags comes from a random stratigraphic level of the site too. Okay, I don't know what that green thing is, but anyway, we're going to ignore it. Here is some of the things that we were finding from the Beaver Creek Rock Shelter. So over here we have some frog and toad elements. We found a lot of fish elements also, which indicate that there was some water nearby. So that's environmentally informative. It's kind of blocked off there, but it's supposed to be a ladybug. Anyway, we found a variety of insect taxa as well. And last but definitely not least is the gastropods, which I'll talk about later, but they kind of stole the show here at the site. We also found a variety of mammal taxa. So we had bats and shrews, these kind of little blocky mice over here, voles. There's some of those taxa that came out. Wood rats, talked about earlier. field mice, and then a variety of small carnivores too. So they weren't super common compared to some of the other groups, but there was a good diversity of small mammal taxa that were present at this site. Okay, so now at a glance, let's look at the some of the numbers here. So the results, each student was able to process about 1 gallon bag throughout the summer. That ended up giving us a little under 1,700 specimens. There's a variety of different groups that came out, as I showed. So we had amphibians, fish, gastropods, insects, mammals, reptiles, and plants. And so just at a glance, this is our abundance curve here. So it's showing how many individuals there were of these different taxonomic groups. And as you can see, gastropods dominate. We called this thing Snail City because it was mostly snails. But there was a variety of other elements as well, but they weren't nearly as common. Now, some interesting things happen when we look at this at the different mesh fraction sizes that we were interested in. So you can see over at the top there that gastropods are still dominating the assemblage, but really only in the smaller mesh fractions. So once you get with those larger ones, you're actually capturing more of plant material than anything else. So there is a bias in what you're finding depending on what size fraction you're sorting. The other important thing here is that red line, that's that 1 to 0.5 millimeter mesh size. So again, we weren't even sure we'd find anything from that mesh fraction, from that screen size, and it ended up having more fossils than anything. So that was really surprising. Sorry, the graph's cut off a little bit, but now this is a plot of the taxonomic richness per fraction. So before, that's just like the counts, how many you're getting of everything. This is now taking into account the different unique taxa, I would say species, but we weren't identifying them to the species level. We were looking at higher taxonomic levels. But this is the individual taxa that you're getting within each fraction. And so not only are you finding the most material from that smallest mesh fraction, you're also finding the highest variety of species or taxonomic units in it. And so this is what it kind of looks like in practice. Here's our just some sample containers from a random bag with different fossils. And it's a little hard to see, but at that largest fraction, that greater than 4 millimeter fraction, you're really just getting weathered elements of larger animals, larger vertebrates. And so that can, partially explain that low taxonomic richness that we're seeing in the plot. As you get smaller, you get more complete elements of smaller animals that are identifiable. But over at that smallest fraction, you're really just getting a lot more material and a lot more different critters coming out than in any of the other sizes. And so this is the last plot for this, I promise, but here is a plot of the rarefied taxonomic diversity for each of these mesh fractions. And again, so now we're not looking at just the individual species or taxonomic units that we're finding in each fraction, but also how evenly distributed are they. And we actually see a pretty different pattern here now. When we're looking at diversity, you can see that 4 to 2 millimeter, that purple mesh fraction, kind of intermediate size one, is way more diverse than anything else. And so when you think about what we're seeing, again, remember those smaller fractions were dominated by those gastropods. There was just a lot of gastropods. And so that makes it not very diverse. The other important thing here is with these rarefied diversity plots is we're also projecting how many more species or taxonomic units will we find if we continue sampling. And so you can see by this kind of flattened curve on the dotted lines is that we've pretty much found everything that we need to find for all of those mesh fractions, except for the 42 millimeter one, where you can see that there's still kind of that arcing going on past that dotted line, which indicates that if we kept sampling a little more, we'd probably even find more species. Okay, so what does this all mean? Basically, this experiment that we did over the summer showed us that mesh fractions down to at least 0.5 millimeters need to be picked in order to capture the full taxonomic diversity of the site. So if you're interested in doing any kind of study, or you're looking at community changes in these microfossils, you need to pick, you have to go that extra effort and pick down those smaller fractions, even though it is time consuming. The other important thing is that there is, there is a bias in what you're finding depending on what size you're looking at. So even though the most taxa were present all the way down to 0.5 millimeters, we found that the highest taxonomic richness was in that smallest fraction. you're getting the most material, and you're getting the most diversity of, not diversity, you're getting the highest, the most variety of individual taxonomic units, but you're getting the highest diversity in that intermediate fraction. That's where you're getting a nice balance. So if you're interested in a study where you want to look at gastropods, but also you want to look at the mammals and the fish and the insects, then you probably want to focus on one of those intermediate fractions. Okay, so next steps of this project, we want to acquire more data, right? All of our interpretations are going to have more weight to them if we have larger sample sizes. So it takes a long time. So each summer we want a new student to come in, pick a new bag of matrix, add that to our existing data set, and see how robust these findings are. The other thing that we want to do then is to replicate this protocol on matrix from other localities. So far we've only focused on the Beaver Creek Rock Shelter, but it'd be nice to know how generalizable these results are, right? Other sites have different fossils preserved, different sediments. All that can result in different fossils coming out and different species coming out at different levels. So our next step is to apply this protocol to Richmond Hill Quarry, which is another site in the Black Hills, but it's a different age, it's a little older. It's got different sediments, different fossils. So it'll be interesting to see whether the same pattern holds up or not. And then finally, we need to curate our assorted specimens. So now we have a bunch of microfossils. They all need to get cataloged with numbers so that they can be usable for research. They need to be rehoused into files and bags, entered in our database, and stored so they can be used for different projects. Okay, and on the note of curation, I just want to run through some numbers here. So to date, since the start at least of the NPS fund in May of 2019, we have cataloged, conserved, and databased over 10,000 specimens. And just to put that in perspective, even just entering something, a record in our database, can take up to 30 minutes. You have to enter, we have all these different fields for different information. A lot of time you have to scan associated documents and information and keep that with the record. So that takes a fair amount of time. And that's just the databasing. That's if the fossil is just good to go, doesn't need to be rehoused, doesn't need conservation, which for a lot of time isn't the case. So blow that up by that amount of time, that's how many hours we put into this project. It really is an incredible amount of time and effort. That wouldn't be possible, of course, without the NPS fund support, but also all of our dedicated student workers and interns who are willing to do this work. And so this has resulted in a 74% increase in our digitized collections over those last 3.5 years. So a lot of progress. It's also interesting to note that almost all of that, over 90% of the specimen of the digitization that we've done, the databasing, has been NPS specimens. So we most of the databasing work that we've been able to do over the last few years has only been possible because of the support of this fund. And why is this important? Again, I want to reiterate that digitizing specimens allows data to be easily shareable for students and their projects with our federal partners who help us manage these data, and any researchers that want to come in, either internally or from other institutions and study these specimens. So it's very important. Okay, and finally, I just want to talk a little bit about the cool research that our students have been doing on these NPS collections that are only possible because of the curation work that we've been doing. So over the last 3 years, we've had 5 student projects, so 3 undergraduate research projects, and 2 master's theses that have either been completed or in progress on these collections. And so I'm just going to quickly go over some of those research projects. So first, Christian was one of our student workers, or sorry, not one of our senior research students who did a senior research project, which is a required class for graduating your undergraduate in biology over here at Mines. And so he was looking at the wood rats, as we saw earlier, but instead of looking at, I guess, did I mention that those wood rats, the body size was measured based on their poop? I don't think I did. I mentioned that they poop on their middens, but those metrics actually came from poop, which is great if you have poop, but not all sites preserve wood rat poop. So for example, we have wood rat fossils, but it's mostly teeth. And so we're wondering if we could apply the same method to look at changes in wood rat body size using their teeth instead of their poops. And so that's what Christian was working on here, is tracking wood rat body size change through time at Beaver Creek and comparing that to paleoclimate data sets to see how their size fluctuated through time and with climate based on tooth morphology instead of poop morphology. And so this project was completed in spring of 2021. And we have another student now who's doing a similar but different study. So Ben is working on the morphology of full teeth. So he is looking at changes in full tooth shape, but instead of using that to interpret responses to paleoclimate, he's using it to try to use this metric to identify different full species, both modern and fossil. So he's capturing morphology of the teeth and applying statistical analyses to see if we can use those to identify modern teeth. And if that's successful, then apply it to the fossil record and see if we can identify which full teeth were present here in the Black Hills during the last ice age and more recently. And this is a project that is still in progress. So Ben successfully defended his proposal in last fall, and then this spring he'll be working on actually collecting the data. Another project, this is the last of the three that worked on Beaver Creek Rock Shelter, but we have another undergraduate student, Samantha Schmidt. Her project involved identifying the snail taxa of Beaver Creek. So as we saw earlier, there is a lot of snails. The problem is we don't know what to do with them. We don't know what species they are. I'm not a snail expert. Most of the people at the museum are not snail experts. So our next challenge is to get them cataloged and put away, but we don't know how to group that because we don't know which snail is which. So that's what Samantha is working on here, is finding morphological methods to identify these different snail species, but also using them to reconstruct paleo environments, the Black Hills, over the last 10,000 years. So she's going to be comparing the different snail taxa that are identified using their morphology to the existing vertebrate faunas of Beaver Creek and seeing how they compare and what they tell us about past environments and environmental change through time. And this is, again, another project that's in progress. Samantha did successfully defended her proposal in the fall and will be conducting the actual research this spring. Okay, now moving on to graduate research. So one of our graduate students, Grace DeVault, did a senior thesis, or sorry, a master's thesis looking at fossils from the pig dig. So her project involved looking at the bone chemistry of these fossils to understand the different diagenic processes that led to the deposition of the fossils and how the chemistry of the actual pig dig site changed over time and what that tells us about the fossilization process. And so this was completed in spring of 2021. And we have another graduate student now who is working on fossils from Salamander Cave, which is another Wind Cave National Park site. So Corin is working on two parts to this project. One part is actually sorting and identifying the fossils, which, as you can see here, are a huge mess to start with. So this is, again, a curation issue that's being resolved, getting these fossils sorted and identified so they can be used for research. Then she's taking it to the next step and actually using these fossils for her research project, which is going to be examining data diversity at Salamander Cave. And so she's going to be comparing the diversity of the faunas of Salamander Cave to the diversity at other sites in the Cave National Park, other fossil sites. And this is a master's thesis that is currently in progress. So a lot of cool stuff going on, and it's only possible because of all the great conservation and curation work that everyone's been doing, thanks to the NPS Fund. Okay, and with that, I just want to acknowledge all of the many contributors to these efforts. So first and foremost, the Benton family, Badlands National Park and Wind Cave National Park for entrusting us with their fossils and letting us do all this work. My predecessor, Sally Shelton, for collaborating just to start this NPS Fund that I have now undertaken, and the various students that have helped out that made all this work possible. So thank you all. I'll take questions if there's time. Yes.
You said that what we call pack rats.
Yeah.
Got much smaller. And based on the pack rat I've seen in our cabin, how much bigger did they used to be?
So it depends on what study you're looking at, but top of my head. I think during the peak of the last ice age, they were up to some of them at the population level, right? Not at the individual level, but you're taking the whole sample there. It was somewhere, if I remember correctly, up to about 20%. Nope. Don't quote me on that though. That's a rough metric. Yes.
So you never mentioned that you are a federal repository. So you get a lot of collections from a lot of different places that are federal lands.
Mhm.
How does that help facilitate researchers that are local, regional, national, international?
Yeah, I think that was covered in the beginning.
No.
I think Rachel. Okay, well, yes, we are a federal repository. So yeah, we are entrusted not only the fossils that we have here at the Paleontology Research Lab are not just museum owned. They, as Jeff alluded to, they come from all kinds of surrounding lands, and they come from federal, state, and tribal lands. So we are the long-term caretakers of those fossils. We don't own them, but we are responsible for doing the curation, the conservation work, and that happens because a lot of these agencies, they don't have the resources to manage these fossils, right? A lot of the federal agencies have fossils, just thousands and thousands of fossils and limited space, like everyone has. And so we have a designated facility to store these fossils, and it also unifies them, puts them in one place for this work to be done. So yeah, I guess we are the sort of central point in managing these fossil resources and accommodating different projects. Does that answer your question? Consolidation, I guess, and also
Part
curation.
one. Part two is you have a lot of researchers come in just because of your fantastic fossil collection.
Right, yes, yeah. So we get researchers from all over the world regularly. Yeah, Kevin.
I'm curious about the big. I was showing it in tours, I hear about it a lot, but I don't know anything about it. I'm curious, there's nothing special about it environmentally that makes it kind of concentrated similar like plant side or something, or is it just a nice horizon where they're all distributed? What is it? Makes that so special in such a volume of stuff?
Sure. I'll actually hand this one off to Rachel. Rachel was the park paleontologist who oversaw the pig dig, so she could probably explain this a lot better than I could.
Nate, could you repeat the question for me? I'm having a little bit of a hard time hearing the audience.
Sure. Kevin, can you repeat it, please?
Yeah, so I don't know where to stop. What makes the pig dig so special in the sense of it's a very fruitful source of fossils? Is it something that environmental that has concentrated them all there, like the mammoth site? Or is it just a really lucky area of horizon stratigraphically that has kind of contributed to this entire fossil collection?
The Big Pig Dig was discovered in 1993 by a couple of photographers visiting the park. And the reason why it's such an important site is because of what we call taphonomy, or the preservation of fossils. It had over 19,000 specimens collected there over the span of 15 field seasons. It was believed to be a watering hole, and the animals were attracted to that area to drink. It was probably a mild drought or a drought type setting. And another name for the site is the Pig Wallow site, meaning a lot of the fossils there were from animals that were trapped in the mud from the watering hole. So you'll have vertical preservation of limb elements. You'll have articulated neck elements. And probably the Archaeotherium was probably coming in to scavenge a lot of the other mammals that were preserved at the site. Some of the other types of fossils found were Mesohippus, which was the fossil horse, Leptomyrix, which was a deer-like fossil, and Subhyrachodon, which is an early rhino. So many of those animals, kind of like the mammoth site in the sense of that they were attracted to the area to get a drink, but they were caught in the mud. Although the mammoth site, much younger, is more of a karst feature where they fell into a sinkhole. So a little bit different geologically, but very important in terms of the preservation of fossils there at the site.
Thanks, Rachel.
No problem.
Other questions?
So when did the pigs die approximately? What geological time period? And is that close in time to when the mammoths died at the mammoth site?
Yeah, great question. In hindsight, yeah, we probably should have put all these fossil sites in time context. So for the pig dig, this is going to be what we call the Oligocene, which is roughly halfway between today and the dinosaurs, about 35 million years ago. So still pretty far, and you know, in that sense, mammoths and us are like blink of an eye. We're basically at the same point in time almost, whereas these pigs are, you know, 30 million years old, or 30 million years older than, you know, mammoths, but also like 30 plus million years younger than dinosaurs. So they're kind of right in that kind of mid zone there. That's what I always say to people, is it's halfway between us and the dinosaurs. That might not be exactly true, Rachel, sorry, but it's a rough approximation, I think.
Oh, yeah, the pig dig's about 33 million years old.
I thought about 2 million.
Who's counting?
Within 1%.
I study those small mammals from more recent times, if y'all can't tell. So. Other questions? All right, well, thank you all again for coming to this talk. We appreciate it. Thank you, Rachel.
Thanks, Nate.
Thank you both. I just wanted to thank everyone again for coming and let you know we do this every third Tuesday. So the next presentation will be on January 17th. And it is all about the Black Hills Astronomical Society, which was founded approximately 70 years ago. And it has currently 2 observatories, I believe. One is just outside of Rapid City and the other one is in Quinn, South Dakota, which is the Badlands. And they're going to talk about what they've discovered in the past 70 years by looking at the sky in the Black Hills. So it should be pretty cool, pretty pictures. Yeah. Hope to see you January 17th at 6. Thank you.